Hi, my name is Yotam, and today I want to present a work with Iriti Noor on characterizing agreement tests. Agreement testing is a very important concept of property testing that appears everywhere in PCPs, low-degree testing, and so on. I will define it in a couple of slides. Let me just say that the work I'm presenting today is based on two papers. The first paper, titled Agreement Theorems for HDXs, high-dimensional expanders in the low acceptance regime, the role of covers, is all about characterizing these tests and understanding when we can get a very strong notion of soundness for them. In the second part of the paper, we use this characterization and further develop tools to analyze a very concrete agreement test on what's known as a hypergraph called the spherical building. But before we get into any of this, let's even define what agreement tests mean. Basically, agreement tests are a way to sort of take a lot of partial functions and local data and stitch them up to one global assignment. The setup that I'm going to present was first given by Goldreich and Safra in 1997. So in this setup, suppose we have some hypergraph with a finite set of points V and hyperedges or subsets capital S of V, which let's think of all having the same size k for the sake of the presentation. The object that we want to test are what I will call sets of local functions. So a set of local functions is a set that has one function per hyperedge little s inside capital S. These functions are only local functions or partial assignments, namely f subscript s is only defined on the points of S and not on the whole vertex set. It's defined to some finite alphabet. We don't really care about what this alphabet is. What we want to understand in agreement testing is whether these local functions actually correspond to one function on the whole vertex set. So we call a set of local functions global if there exists a function on the whole vertex set so that every f subscript s is actually just taking this g and restricting it to the points of S. These are what we call global functions, or sometimes we call them direct product functions. Agreement testing, or direct product testing, looks at these objects, only probes a couple of random f subscript s, and is supposed to give at least an approximate decision about whether this property holds. So, more formally, what is an agreement test? Given some distribution, D, over pairs of hyperedges, we define the agreement test that D induces by the test where we sample two sets according to D, and we accept if the corresponding functions agree, namely assign the same value, for every vertex inside the intersection. For example, if I were to sample these two sets, I would accept if the corresponding functions agree on their assignment to B and on their assignment to C. I think this test is kind of natural because if you actually have a set of global local functions, then these two values are indeed equal because they're actually only equal to the function g at that point V, whatever that function g is, but it's defined everywhere. So our goal in this area is to design these triples of a hypergraph and distribution so that sort of a converse or a very strong converse notion also holds. Namely, if the test passes with at least some, say, constant probability, then we will be able to say that the set of local functions is non-trivially correlated with some function on the whole vertex set. Namely, that there exists a function so that for as many as possible little s's inside capital S, f of s is actually the restriction of this g to s. You know, it's equal to it on all points. So just a quick example to see that we're on the same page. Suppose I named these subsets in the hypergraph S1 up to S4, and I look at these four functions. Of course, every function here is not defined on the whole hypergraph, only on a small component of it. We can see that if my distribution were to sample these four pairs, then I would pass the test. For example, for S1 and S2, because they agree on their assignment to B, then I would pass the test, and so on and so forth. Note that S1 and S4, I colored it green because S1 and S4 don't even intersect. So technically they agree, but of course we're not checking anything. Of course, in the other pairs, we have vertices that disagree. So if I had a distribution that chose one of these 6 pairs uniformly at random, then the probability of passing the test would be exactly 4 out of 6. But what does this even mean? What is the precise notion of soundness that we want this agreement test to have? This is the notion of what I'm going to call delta epsilon soundness. Basically, a triple like this is called delta epsilon sound if whenever a set of local functions passes the test with probability at least delta, this implies that there exists a function on the whole vertex set so that for at least an epsilon fraction of the hyperedges, f of s is equal to g on all the points of S. Let me give a quick example of an agreement theorem that was proven in the early 90s. So in this setup, our vertex set V is some finite vector space, fp to the n, where p is some prime power. Our set of hyperedges is going to be all the affine lines inside this vector space, and our distribution is going to sample uniformly 2 lines that intersect on a point. So no parallel lines allowed. A theorem by Rubenfeld and Sudan from the early 90s says that if we have a set of local functions, namely one function that is only defined on some affine line S, and if we know these functions are low degree, and more importantly, they pass the agreement test 99% of the time, then we can find some g on the whole vertex set that is in fact also low degree, so that for 98% of these affine lines, f of s is equal to this low degree function g on all the points of S. Note that this is not exactly 98% soundness as we described before, because we are restricting ourselves to sets of local functions that are also low degree, so like linear functions or quadratic functions and so on. I'm hiding some technical details here, but other than that, this is roughly what it means to be 98% sound. In fact, we can even extend this theorem further. A theorem by Aurora and Sudan says that in the same setup, if we know that the functions pass our agreement test even with 1% probability, this already implies that there exists some function on the whole vertex set that, well, maybe it's not equal to all the f of s's or most of the f of s's when we restrict to a random s, but it is equal to f of s at least, say, some small constant % of the time. Again, this is slightly informal. I'm hiding sort of dependencies on this field size and so on, but I think that already this is interesting by saying that even if we pass the test a small fraction of the time, we can already find some inner structure in this set of local functions. This setup of 1% soundness is precisely the setup that we looked at on our work. Why is this setup so important? First of all, let me just make clear that when I say 1% soundness, I mean delta and epsilon soundness when these delta and epsilon are small constants. Sometimes we even want to take delta to be subconstant in various parameters. But for now, let's just think as, delta being 1% and epsilon being, say, 0.1% or something like that. This setup is extremely important in many applications. I think the first application that comes to mind is the parallel repetition theorem that was proven by Raz in 95 and then improved and extended in various ways afterwards. Basically, this theorem says that we can take a PCP with low soundness guarantees and transform it to PCPs with high soundness guarantees using some agreement test that is 1% sound. The second application that I just want to mention is low-degree testing, which was where the theorems that I mentioned before actually originated. Low-degree testing is basically a property test where you probe a truth table of some function and is supposed to decide whether this function is close to a truth table of a low-degree function in Hamming distance. I don't want to get into this, and I also don't want to exactly say what the third application is, but basically the 2-to-1 games theorem is a very important theorem in hardness of approximation, where also these agreement tests are analyzed. Just a brief and very partial history. In the early 90s, agreement testing, and in particular this 1% soundness regime, was sort of analyzed implicitly in many PCP and low-degree testing results, but only in 97, I think, Goldreich and Safra defined this as sort of a first-class problem. After that, in the 2000s, there came results on specific hypergraphs showing that they are 1% sound, and also sort of extending these tests in various ways. Examples include the complete K-uniform hypergraph, or hypergraphs that come from subspaces of vector spaces that somewhat resemble the example that we saw before on these lines and planes hypergraph. However, in our work, we try to ask a more abstract question and characterize when is a 1% agreement test actually sound. The word characterization may not be especially mathematically rigorous, so I should say what our goal was. The goal is to construct 1% sound families of V's, S, and D's, where the number of sets S is linearly proportionate to the number of vertices. This is sometimes called the sparse or the randomized agreement test regime. In previous results, the examples that I talked about before were either looking like this, where the number of sets grew like the number of vertices to the power of the set size, or something like this, where the number of sets was a small polynomial of this number of vertices. This is by Impagliazzo, Cabanets, and Vigderson. I should say though that in this case, the set size itself grows to infinity, which is kind of weird when you want to use this in applications. The goal in all this area is not, just purely for fun. We want to de-randomize PCPs and other property tests that use agreement tests as sort of inner gadgets or as things in the analysis. We can imagine that if we use such an agreement test in a PCP, the fact that we have a few number of sets will allow us to write maybe a shorter PCP or use a more de-randomized verifier for it. However, to do something like this, we need a more abstract or a stronger method for actually constructing and arguing about 1% soundness of agreement tests. So without further ado, this is precisely the result that we had in our first part of the work. So if we have this triple VS and D, that first of all comes from what's known as a high-dimensional expander, which I will define in about 2 slides, and also has a topological property that is named the no small connected cover property, then our triple gives rise to a 1% sound agreement test. This theorem was proven both by us and independently by Mitali Bafna and Dor Mintzer that also have a paper on this in STOC. Even without knowing what these things is, and I will say what they are in a couple of minutes, I should say that this theorem moves from a computational question about agreement to a combinatorial and topological characterization of these things. This is saying that if the hypergraph has some spectral properties and it looks so and so and its topology is something, then you can say that it has a 1% sound agreement test without, actually looking at the functions and so on. This thing gave rise for a method for constructing or arguing about 1% sound agreement tests. In fact, recently, we used this theorem to construct 1% sound agreement tests where indeed the number of sets is linearly proportionate to the number of vertices. This work is together with Alex Lubotsky and also was done concurrently by the other research group, Mitali Bafna, Noam Lifshitz, and Dor Mintzer. The second part of our work was to actually use this theorem to analyze another kind of agreement test on what's known as the spherical building hypergraph and to show that it is indeed 1% sound, as we discussed before. I'm not going to even define this thing because it's kind of technical, but you can think about it basically as some kind of variant of this point line hypergraph that we talked about before that comes from subspaces of vector spaces. However, in this setup, our theorem applies for all sets of local functions, not only low degree. This thing is already non-trivially sparse. The number of sets grows quadratically with the number of vertices, so of course these are families of hypergraphs and not just a single one. Using the techniques and ideas in this result, we managed to improve it to the result that we discussed in the last slide. So let's talk about the two properties that I mentioned in our first result. The first is to be a high-dimensional expander. Basically, high-dimensional expanders are hypergraphs that have local spectral expansion properties. Without getting into the definition too much, basically you can define a graph or a random walk using our test distribution where you walk from one set to another set if the pair appears in the support of this test distribution. And being a high-dimensional expander, very loosely, says that this walk expands or mixes very well, even if you sort of condition on subgraphs where you condition on things being inside the particular intersection. It's not supposed to be too surprising that high-dimensional expansion comes into play. In fact, in a work by Dinur and Kaufman from a few years ago, they show that if you have a high-dimensional expander like this, you can get soundness, not in the 1% regime, but in the regime where delta is very close to 1, say 99%. So, again, this seems like a good idea to require this from our hypergraphs. However, we also need a second property that relates to a topological notion called covers. Given some integer m greater than 0 and two hypergraphs, an m cover is a function from the vertices of one hypergraph to the other that has three properties. It is m to 1, so every point here has exactly m pre-images in v tilde. Second property, it is a homomorphism. And the third property is that if you restrict this function to a neighborhood of some vertex here, then it is an isomorphism between the neighborhood of that vertex to the neighborhood of the image. So if we look, for example, at these two hypergraphs and the function that sends a0 and a1 to a, b0, b1 to b, and so on, one can observe that this is a 2-to-1 function. It sends hyperedges that are represented as triangles that contain the three endpoints. You can see that every triangle here is mapped to a triangle here. Finally, if we look, for example, at this vertex v0 and on its neighborhood, we can see that rho maps it isomorphically to the neighborhood of the image B. Turns out that we need to require from our hypergraph V and S that it will have no small covers that are connected. Namely, and this is a lemma that was also proved by us and by Bafna and Mintzer, if you have a connected M cover, then you will get no soundness for delta which is equal to 1 over M. So just to be clear, if you have some hypergraph and you know existentially that there exists a small connected cover for it, then you can deduce that no soundness of agreement tests are possible no matter what the distribution is for delta which is equal to 1 over this M that is a parameter in the cover. I'm not going to get into this, but basically the idea is to sort of confuse the agreement test here using a global function that actually belongs to here. Just one slide about ideas of the proof of the first result that does sort of the converse and says that if we are high-dimensional expanders and we don't have any connected covers, then we can actually deduce soundness. One of the main ideas is that in algebraic topology, it is well known that this notion of covers corresponds to a particular type of constraint satisfaction problem called a unique games instance. So these are constraint satisfaction problems, like 3 coloring in a graph and so on, only the constraints there correspond to permutations. So basically what happens is we take a set of local functions that agree, at least a non-negligible fraction of the time, and we use them to construct such an instance of unique games, and a lot of our work is to show that this thing is solvable, or you can find an assignment that satisfies most of the constraints, and that the solution actually comes from a global function. Unfortunately, not a global function on the hypergraph where these are defined, but a global function on its cover. However, using the no connected cover properties, we can sort of project it back to a global function on the original hypergraph that agrees with our local functions, at least with some non-negligible probability. Let me just throw out one more idea that appears in this proof, which is this idea of coboundary expansion. This was defined by a mathematician named Gromov and also by Lineal and Meshulam, I think in the early 2000s, and it basically said something about the topology of the hypergraphs, but we can interpret it as a stronger version of this equivalence between covers and unique games instances, and this is in fact a crucial component in our proof. Thank you for listening.